Okay, then today we'll discuss on screw jacks. I assume personally that you are already familiar with quite a lot of concepts that we discussed earlier. Okay, at least angle of friction, what it is, how normal and friction forces are related that way. Okay, so if you know that, I think you can understand screw jacks quite easily. Over here we'll not just discuss screw jacks. Screw jack is something of very much importance because it is used widely in the industry. Okay, so but we'll stick ourselves to something which uses this type of thread. It is not just in screw jack, it is at many other places as well. So we'll see as we go. Okay, so yes. Okay, so there are two types of thread primarily. There are many others though. So in this type of thread, you have seen, you have if you open up anything which are like this, let me open up one. Just open up your pen if you can see. Okay, if you have a pen in your hand, just open it up and you can see there are threads here. Okay, you might have realized that there are threads. Okay, and that could be a V type of thread and it could be also of a square thread. So just check it. Okay, you just try and open it up. Okay, so mostly they are V type of threads in your pen. Basically this type of thread has an angle between adjacent flank. What are flanks? If you look this closely, let me zoom it out. Okay, if you look this closely, okay, so there is an angle between flanks. So this is one and this is one. Adjacent one, there is an angle. Okay, so that is what an angle that I am interested in here. Okay, so okay, get back to the normal zoom. Okay, so there is an angle between adjacent flank or the thread angle. This is also known as thread angle. This is also known as thread angle, and what it is? It is in between 30 to 60 degree. Okay, so this angle varies from 30 to 60 degree as such. Okay, but not necessarily in case of BSW thread, that is British Standard Whitworth thread. It can go up to 47.5 degree. It is standard. In case of BA threads, British Association thread, there is BSW, British Standard Whitworth thread. So there are many types of standards that are followed world around. Okay, so but this will always be within this much. Why it is so, that we'll see later. Okay, it is used as fasteners. Fasteners due to high strength. Fasteners, what are fasteners? Like common nut and bolt, that is fastener. Studs that are used, okay, as a tie bolt in IC engines. So that is also fastener that ties your cylinder head to the liner. So there are many other fasteners. It is not that it is using some sort of adhesive or a glue. Okay, but this is a fastener because it is sticking two different bodies together. Okay, and that is why it is still called as a fastener. Because it is low cost, easy to manufacture, and it is widely available. Because it is easy to manufacture, it is widely available also. Okay, common lathe can do this. Okay, so that is why it is very, very common. And the idea behind why it has propagated that much, because it is stronger. You see, it has wider base. Okay, this is very wide. So where is the one which is not wide? I'll show you that also. Okay, so this width is the base width is very, very wide in case of this type of thread, and they are stronger. They are grouted to the main cylindrical surface with a very strong binding. So that is why it is stronger. So low efficiency because it has high friction. Friction helps this one. Why? You are going to use this as fasteners. Once it is tightened, you don't want it to open it up automatically, right? So that is the reason. And because of that, it has high friction. And that is the reason why it cannot unwind so easily. Okay, easy to manufacture, that is why you find it in mass scale everywhere. Radial pressure is present. Radial pressure is present. That is something we don't want, but it is there, doesn't matter. Okay, if you apply load onto this, okay, so that load gets transmitted in two directions. First, it will be, if it is an inclined surface, you apply load vertically like this. So it has two components. It has two components. This wedge, this is something like this. It tends to go in. So that is compressing the surface on which this thread is there. Okay, and a part of this will go and hold it. Okay, this load will be supported on this surface by an inclined thing, and that is the reason why it is creating this compressive stress on that. So that is something which we don't want, but it is present. And yes, so radial pressure is present due to thread angle. If this angle is straight, that will be not there. Okay, so let us say you have a thread in which you have square threads. So if you apply load like this, there won't be any radial pressure. Okay, so that is absent in case of square threads. So let us talk about square threads also. So what is this type of thread? In this, the flank are perpendicular. Okay, flank are perpendicular to the axis of thread. So if this is the axis of thread, you have flanks which are like this, is it not? So that is how it look like. So this is how it is arranged, an angle between two adjacent one. Yes. It's okay, I think. Yes. Okay, so this is something like square thread. Square thread, what happens? You see, you have these adjacent faces. They are parallel to each other, and angle between them is 0 degree. That is what is known as a thread angle also, and it is 0 degree. So in case of square thread, that is there. So this is how it is constructed. It is used as a power screw. What is power screw? That is used to transmit high power from one end to the other end. If a screw is rotating, it can be converted to a linear motion, like a tool post in case of a lathe. Okay, tool post. Sometimes they are automatically winded and it keeps on rotating and things goes moving. Okay, so that type of arrangement is there in case of lathe. I'll show you at time. Okay, so that is there. So it is also used as a screw jack, the big pictures that I showed you right at the beginning. So those are the screw jacks. It is used to lift maybe cars, maybe truck, to replace your wheels, to do some maintenance job. In presses it is there sometimes as a C clamp. If you have seen C clamp, C clamps are something like this. Okay, and it has a thread somewhere like this. Okay, and it can hold something. Okay, so that is a C clamp. It can hold something. Okay, so it is used in those sort of clamps. Vise, table vise, that is used to hold an object and you do some maintenance on that. So table vise also uses this type of, so you have seen it is used to transmit power, rotary power to a linear motion, rotary motion to linear motion, and it can have self-locking thing also. So we'll talk about self-locking once again here. Okay, once it is tightened, it doesn't automatically unwind itself. So what is the condition, what are there? So that we'll talk about here also once again. But they are weaker because they have pitch 50%. So what is pitch? First of all, what is pitch? That is distance between, yes, somebody said something. Yes, two adjacent same type. Yes, so yes. So distance between this and this. If I zoom it further, so you can see this. So this becomes your pitch. Okay, distance between two consecutive thread is your pitch. Got it? So, and that is equal to half of the So width of the base is equal to half of the pitch. So that is why it is thickness is little less as compared to this one, okay, as compared to V type of thread, and that is the reason comparatively with the same diameters type of, with same material, this is a little bit weaker, okay. And they have high efficiency because it has low friction, but it is difficult to manufacture using standard techniques, okay. And absence of any radial pressure is there, that is why it is more popular. So your load is directly transmitted in one direction, that is in linear towards the axis of the thread itself, okay. So that is the reason. So you can directly transfer the load instead of getting it split in two directions, it is transmitted to single direction. So this is something of interest that we'll cover now, okay. That is known as square thread. So we won't be covering much on V thread now, okay. So let us begin analysis of that, okay. Let me show you a visualization of this. So this is something that I have prepared for you. This is a CAD of such thread. If you can see this, it starts at one end, gradually it goes something like this, okay. So this is how it look like. Hope you can see this, okay. So this is how this type of thread are, okay. I'll close this one, I'll go back to my original thing. So now we'll do some analysis and we'll see a little more type of square threads or any thread to say, okay. So I want you to focus on this one, these two figures. So what is this one? Just one single thread is starting, okay. Single start is there, it covers whole of the distance, okay. And single one, if you can follow one of them, you will start here, you will go here, you will go here, and one by one it was done. So this is a single start thread, but there is a possibility that you have double start. What is that? What is that? So if you follow one of the thread, you will start here, you will go behind, come back here, like that, okay, like that. So every alternate one is one single thread. So what happens to this one? Where does this begin? This begins at, let us say you have two starts. So they will be starting at one over here, other one at 180-degree apart. If you have three starts, they will be at 120-degree apart. Got it? And then if you can follow one of them, you will start here, you will go here, you will go here, and so on so forth. Okay, so that is how it is made. So this is known as a twin start threads. Twin start threads. There can be multiple start thread also. So in your pen, in your standard pen, if you can open this one, okay, if you can open this one, you will find mostly they have two threads at least. Okay, so what is the benefit of that? It makes you travel faster at the same time. At the same time, because of number of threads are more, it can carry more load. Okay, so that is the beauty of having such multiple start thread. You can travel at a faster distance, but it can carry more load. Okay, if you want to travel at a faster distance, you have to make your thread more inclined. In that case, the load that is coming from the top gets diverted. So that is what we don't want. Okay, so what you want to carry more load, you can have two independent threads, which each of them having more inclination so that you can travel more. So anyway, we'll go more into detail later on. Okay, but now we will begin like this. Just a sec. Okay, so we'll start our analysis now. So what you can see here, I'll first explain the terminologies that will follow for this analysis. Okay, so what is this? This is L. That is the lead or advancement per revolution. Advancement per revolution. If you turn by one number of times, how much you advance. So it is here. You can see this. So in case of single thread, it will be equal to the pitch, okay, this pitch, that is what you can travel. So let us say you have two starts. You have two starts. So lead will be equal to 2 times of pitch, right? In case of this thread, the one which is down below, so you just by one revolution you traveled how much? Twice the pitch that you can see. Pitch is the distance between two different consecutive threads. Okay, so you will cover this much. So this is what L is the lead, N is number of starts, pitch of the screws. So if you have pitch, N is number of starts you have, so lead is, that is per revolution how much you advance. So it becomes directly equal to this. So hope this is quite clear. Yes, very good. So yes, just keep acknowledging in a short while, okay, so that I keep assured that yes, you are understanding. So anyway, so what is R? R is the mean radius, mean radius. So it has minimum radius, that is this, okay, this surface, and it has maximum radius, that is this surface. You agree? So these two are the surfaces. So both of them has different radii. Okay, so what is mean radii? It is exactly the mean of that. So that is what is mean radius. Alpha is the helix angle. This is helical shape. Okay, so that is the reason you call it helix angle. So that, what is that? If you just make a tangent, let us say you are at this point. Okay, you are at this point, you can draw a tangent on that surface and the horizontal, this is the angle that is known as helix angle. Clear? Okay. What is mu s? It is the angle of friction. Mu s is angle of friction. Okay, this will be using, because we assume this is not frictionless, it has some friction, and it has to have some friction because we don't want it to unwind of its own. Okay, pitch is the axial distance between two adjacent threads. W is the axial load that is supported by the screw. This is the load that is coming from the top. Got it? So this is the load that comes from the top, and that is what it is carrying, okay, over this. So this is one construction. There are many arrangements, but it goes directly on top of this thread. Okay, so and what is R? R is the reaction exerted by the jack frame, reaction exerted by the jack frame. So this is the one. Okay, so this is the one. Okay, we'll see why it is directed like this, what are different things that we need to consider here. Okay, so we'll discuss on this R specifically. Okay, so what is P? P is the effort, external force acting on the jack arm. This is where it is acting. Got it? You can see this. So this is creating a moment that tends to turn this thread. So P acted at a distance A is creating a moment about this axis. Is it not? So P into A is the moment that is trying to rotate this thread about its axis, and simultaneously you will get a lift. That is what is expected. We'll see how it happens. Okay. So that is there. So let us move ahead. What is Q? It is the effective horizontal force on the thread. Effective horizontal force on the thread. We'll see, we'll open this, we'll try to open it up in a planar way. Okay, so that is what is Q. We'll see how it works. So if it is P into A is the moment, how much is the force that is trying to lift this load on this? So this is like an inclined plane. This is like an inclined plane. Do you agree? On which you are trying to ride. So if this is an inclined plane, you can assume this load as a block which is trying to ride upon that. Okay. So how much is this force which is trying to lift it up? If you can get this, or else I have a better picture of it, we'll come to that. So if this is the force which is trying to lift this load upward towards this plane, okay, if you unwind this, if you open it up, because you know friction is not dependent on the surface. It is only dependent on the load that is coming on any plane. This plane is an inclined plane, inclined at an angle alpha. So this load is acting on top of this surface. Okay, so there is a load, that is the load. So this load is getting lifted upward this plane by a force Q. So how much is that Q? We'll see. So it can be written as this. Do you agree this? P into A, P into A is the moment that is acting to about this axis. This is clear. So same moment you need to balance it out. So where is that acting? It is acting by a load Q at a radial distance. How much is that distance? It is at a distance which is mean radii of the surface. Okay, so this surface. So it is mean radii over here. So it is acting exactly like this. So there is a Q that is trying to move something like this. Hope it is clear. We'll draw it once again, don't worry. We have a better picture next. So, but now that it is, because you cannot take the maximum radii, you cannot take the minimum one, you have to be somewhere in between. Okay, so the force varies maximum at one end to the minimum at one end, and it varies linearly. It varies linearly, so you take it mean. Okay, so that effective distance is r, and the mean force is this. Okay, so that is why it is like this. So we do analysis with this only. Okay, so analysis is, yeah, you can take it like this. Yes, 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 you can take it like that. But these are very small. Okay, so it is not that relevant actually. These width is very small. Okay, so but any case it has to be like that. So analysis is unwrapping this thread by one turn. You open it up. Okay, similar to a block on an inclined plane. That is what we are going to analyze. So how much distance that this block will travel in one complete turn? It will be 2 pi r. Yes. So if you open it up, if you open this thread and unwind it, so you will get how much? It is 2 pi r distance. So that is the distance covered by any load on this surface. Okay, on this surface. So if you zoom it out, okay, so on this surface, this is your mean radii. Okay, this is your mean radii, and if you go just by one turn, how much you will travel? You will travel by 2 pi r distance, is it not? If this is r, so if you rotate by one combined complete turn, it is approximately equal to 2 pi r. So that is what we are saying. Okay, so if you open it up, that is what is the distance. L is the distance lifted vertically upward per turn. L is how much? Yes, it will be greater, but because the pitch is very small as compared to the radius, so that is why that distance is almost 2 pi r. Okay, okay. So pitch is very small as compared to the radius. Most of the time you can see anywhere. Okay, so that is why. So 2 pi r is the distance traveled per unit ton by that load that is lifted, getting lifted. Vertical distance that is traveled is L, this one, pitch. So vertically it will ride that much. Okay. So if you open this thread, what you can see, now I'll show you a bigger picture of this. So this is how it will look like. So I have unwounded one of my thread like this. Okay, and what I see, this is the distance which this load is traveling. Okay, this is for one complete turn, horizontal distance opened up, and this is the lift that load has seen, vertical lift. vertical lift, right? So this is what is the vertical distance that it has traveled, and this is what the slope, if you define helix angle is exactly this much. So it is L by 2 pi r. If you can see this again, oh, let me clear it up. So this is your helix angle. You can see this helix angle, this helix angle, this one. Okay, so this helix angle is exactly that inclination angle that takes you in that type of surface. So vertical lift is L in one complete revolution, and 2 pi r is the horizontal distance that is traveled, alpha is the helix angle. Okay, so hope you got how we are going to analyze this now. So this becomes now our standard inclined plane and a block problem. Okay, so now we can analyze the way we want it. Forget about thread anymore. Okay, so this is what we are going to do. Okay, so using, yes, 2 pi r, if you see a spiral now, I'll draw it here in more clearer way. So this is your spiral. This is how it goes. Okay, so if you turn by the mean distance is r, mean distance is r. So if you start from a location, if you start from a location and to a same location in one complete turn, you lift from here to here. Do you agree this? If you rotate in, yes. So this is what was your L. Clear? This is your pitch. Okay, in case of, let us consider just one pitch now. So this is the distance that you are going to travel. Okay, so this is your vertical lift that comes here. How much is the horizontal distance that you have traveled from here to here? So this is the distance from here to back again. So if this is r, so this distance will be 2 pi r approximately. Is it not? So it is like a ring. If you cut it from a place and stretch it a bit, now you get it. You just open, take a bangle in your hand, okay, metal bangle, okay, break it up in between, okay, and then just pull it. So what you see? You see something like this was your this. You cut it here. If you pull it, how, what you will get? You will get something like this. So this is the distance. It hasn't changed. It is still 2 pi r. Okay, and this is what you have pulled. So that is L. So now it comes like this. Hope you got it. Hope you got it. Yes, very good. So that is why if you, yes, yes. See why this is taken, no? It should be like this, but effectively that is a projection. See, that is a projection which is 2 pi r. It won't be that. See, once it makes a spiral now, so if you project that spiral, if you look from the top, it is a circle. Is it not? This is a circle of radius r. So if you look from the top, it is circle. Actual distance is more. This distance is more, as you have said right initially. Okay. So if you project this spiral, look from top, it is a circle. So that is why this is 2 pi r, not this is 2 pi r. Got it? Very good. So hope you got everything about this. Let us not waste time over here. Okay. So that is why. So giving an example of a bangle just to make you understand, that doesn't mean that 2 pi remains there. Actually, it is, if you look that bangle, broken bangle from the top, so mean radius of that is r, and that circle is of 2 pi r. That means that projection is 2 pi r, not this inclined one. Okay. So this is the vertical lift, this is the horizontal distance, this is helix angle. So it is all opened up figure now. I want to analyze it. So let me do it. So I have transferred my weight now. transferred my weight over here. How it happened? So external moment that came onto this, due to arm there was a force which was P, so moment that came here was P into A, right? So if you see it in this way, you have a block that is trying to get lifted on this plane. So where is it? It is at a distance r, is it not? Is it not? So that block is now seeing a force of Q. That block, let me not make it more puzzly here. So I'll draw it once again. Okay. Today we have enough time, so let us do it. So this is your, I'll extend little more now. Okay. So this is your opened up. So this is a block which is trying to get lifted from here to here. This was the distance that we reached. This is 2 pi r, that is the projection that we have traveled. Okay. Projection was 2 pi r. This block is getting lifted. So this is the force that acts on this, and I call it as Q. Okay. So externally the moment which is created actually gets transferred to this block which is getting lifted. Okay. So and that is acting at a distance r. So Q into r should be equal to P into A. So effectively Q is equal to PA by R. A is known, R is known. So that is P, that is the load you are trying to apply from external agent. Okay, so this is the external force that is acting. So effective force that gets transferred to this load is Q. Okay, so hope you got it now. So this is Q. W is the vertical weight that is like this. Okay, so this picture is quite clear, I think. So let us move ahead. Let us move ahead. Okay, so hope you got it. So this is what it is. So alpha will be equal to tan alpha will be equal to L by 2 pi r. This is quite trivial. We'll move ahead. So alpha is the angle made by psi s, is the angle made by r with the sliding surface normal. This is quite okay. This is your normal. This is your normal, right? And you are trying to lift it up. So definitely you will have a friction force which is like this, which is trying to oppose that motion, is it not? So that is why this R, this is angle of friction, static friction, it is about to slip. Okay. So this is the maximum sliding friction. Okay. So that is why it is psi s over here. So it comes on top of alpha. This is your normal direction. Okay. This is your normal direction, surface normal. Okay. So now you can resolve all your forces. Now R sine alpha plus psi s is equal to Q. Cosine of this will be supporting this W. Cosine, that is this one, will support this. Sine A will support this. Clear? So using this two, now I will move ahead. I can write this, and ultimately moment is equal to QR is equal to W into R. So is it quite okay? QR, I have just substituted Q from here. From here Q is substituted here, you got this, and then you can extract alpha should be equal to tan inverse L by 2 pi R. This is the moment, which is required to lift the load. M is what? M is the moment which is required to lift the load. Okay. So if you know how much, let us say it is 200 kg something, you want to lift it, so you have to apply this much of moment. Okay, that is Q into R. So if it is asked that yes, there is a lever which is having a length of 10 centimeter or 20 centimeter length, so how much force you have to apply? It is equal to Q into R should be equal to P into A. This is your 10 centimeter. Okay, this is an external load. R normally will be given also in your question. Okay, so that is the dimension of your thread. So this is how it is analysis for lifting of the load. Okay, assuming that load is sliding upward on this inclined plane. So this is the way we analyze things. Okay, so now going to the, yes, yes, please. No, 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 no. You saw it wrong actually. If you look from the top, how was that? Q is the weight which is trying to be lifted. Let us say this is the block which is here. This is the block. You are applying this Q tangentially and you are trying to make it go like this. Okay. So this is how. Yes, yes, it is Q is acting, this is the block, Q is acting tangential to this, not tangential to the surface, rather it is horizontal like this. Okay. So now hope you, why? Because there is no contact that is there. Whole of the weight that comes on this, how come that weight will go like this? Because you are having load that comes from the top. If it is from the top, this surface will create friction, not this surface which is parallel to it will create friction. So then what about this centripetal force? Centripetal, where did it came? It is not rotating at that high velocity. No, no centripetal will come. It is not a free weight. See, first of all, you try to understand the situation. It is not a free weight. Now, if you can see this or earlier picture, the first one, how was that? It was not a free weight. You see, if this external cage rotates at very high speed, how does it matter? Okay, so it is not going to have any centrifugal force. Even if it is there, how does it matter? That is not going to deform, right? So centripetal force, there is no question. It is quasi-static system. Do you understand what is quasi-static system? System is in analysis, it is at rest, it is not moving. So there is no velocity. You are applying a force and it is in a balanced condition. So I want to analyze that. And why I am interested to analyze that not in a motion? Because while it is in a motion, you will already get what? That is a friction which is lesser than static friction. So if static friction is analyzed, rest friction will deal with in no time. Is it not? So we want to statically analyze this system. Okay. So that is why. So anyway, so let us move ahead. So now we'll do analysis of lowering. Lowering means you are unwinding the thing. You want to put it down, bring it down. So in that case, force, effective force will act like this. Okay. Q will have no role later on. You have to deal with the moment. Moment is equal to Q into R. External was like this. So most of the time you will deal with this external force creating a moment. Q is just for the analysis purpose. Okay. In end result, you won't find Q. In end result, mostly you don't find Q. So this is the moment that is given by load, radii, and angle of friction and helix angle. So those are the things which are to be of interest, right? So that is what QR is internal moment that is generated because of external load. Okay. So again we'll start moving now. So this is your block which is moving downwards now. This time friction will be from opposite side. So that is what is making this like this. So this is your static friction angle. Static friction angle, this is your alpha. Okay, this is your alpha. Got it? Static friction angle, this is your alpha. Alpha is directly normal that makes angle alpha because this angle is alpha. Okay, W is the load. So this time if you equate the vertical and mind it, alpha is less than static angle. Why this is required, you tell me? angle of repose, if you remember, if alpha is greater than this angle, you don't need an external force. It will automatically come down. So that is maximum helix angle. After that, with that load, it will automatically start falling down. Okay, so we assume that is less than that. That is why you need an external force to move it. Okay, so again I have used this angle basically, that is resultant of psi s minus alpha, and taken the horizontal and vertical projection, equated it to W and Q, right? So that is what is after equilibrium condition. If you analyze, again you got a similar equation, similar thing. This time you saw tan phi psi s minus alpha is equal to Q by W. Again it is alpha is turning out to be the same, but moment this time there is a negative sign here, that is to be remembered. While lowering, that is negative, while raising it was positive. Rest everything remains the same. Okay, this will be required for doing numericals and all. Okay, so that is why. So again, this is the moment required to unwind the screw or lower the load. Limiting case, what is the limiting case? Limiting case is when alpha is just about to slip. That is the limiting case. Okay, if alpha is greater than that, it is not a self-locking thread, then it will automatically unwind. So in order to be in a self-locking region, this alpha should be less than this angle. So this is the state of self-locking. Okay, so once it is tightened, it cannot unwind itself. Okay, because psi s is greater than alpha. So this is the condition for self-locking of any thread. So this is analysis for lowering. Earlier we did it for raising. Now we'll do automatic lowering. Okay, automatic lowering, or the minimum force that is required from this side so as to hold it. This time I have assumed, yes, psi s is this. I am trying to push it like this, so reaction force is in this direction. Got it? Okay, this is the minimum force I want to analyze for automatic lowering. I'll equate it to 0. Okay, so as to create a boundary condition. Okay, limiting condition. So upon removal of the external moment, so external moment is giving you this, which is trying to hold it in place. If you remove it, okay, if you remove it, how much is that? What is the condition? So that is what we are going to do. Okay, so this is your external force created due to the external moment that is trying to hold it in place. This is angle of friction. This is because of angle of inclination. This is L, this is 2 pi r, everything is as it is. W is the load that is acting from the top. R is the reaction force, that is this. Okay, so load is tending to slide downwards. Mind it, tending to slide downwards the plane automatically. This time impending motion downwards, alpha is now greater than psi s. It is not equal to psi s or that. Okay, so it is already greater than that. I want to hold it. Okay, I want to hold it. So this time the analysis goes like this. So again, force balance, you do Q and W, projections of R along vertical and horizontal directions. Okay, again it gives me something like this. So this is the moment that is required to stop the screw from unwinding by itself. Okay, so this is what is the moment. QR is the moment. This is what is the force. Q is the force that is required to hold it in position. So QR is the moment that is required to hold it in position. Ultimately, QR should be equated to external force P into A, okay, to hold it in place, or just the moment you can call. This is the moment that is required to stop the screw from unwinding by itself. Okay, whole of the figure, all the figures are similar, situations are different, it looks similar but they are not. Okay, I'll share you this so that you can analyze it carefully. So you see this force is shown like this. In our earlier picture it was shown over here. In our still earlier picture it was shown like this. So it looks like same, but it is not. So actual picture is shown here. This is the simplified version of this thread. Okay, this thread simplified version is here. Okay. Okay, so now let us do a small problem on that. Okay, are you ready with this?
Yes, sir.
Very good. Okay, so let us begin. Okay, so this clamp has a double square thread. Mind things to be noted since beginning only. So this is double square thread. That means it has two threads. Okay, and mean diameter, mean radius, it is not mean radius, it is mean diameter. So R will be equal to 5 mm. Done. Pitch is 2 mm, pitch is 2 mm, and it is double sided thread. So how much will be L? 2 into that pitch, so it is 4 mm. Very good. So you can grasp it thoroughly. Yes, the coefficient of friction mu s is this. So when you need mu s, they will give you phi s. When you need phi s, they will give you mu s. That is a trick, you know, so that you use, yes. So this time you need the angle psi s. For most of your analysis, they have given you mu s. So you can easily calculate that. Yes, very good. So yes, so now the maximum couple is 40 Newton meter is applied in tightening the clamp. So this moment that is externally applied, it is 40 Newton meter. So forget about this length A or the force that person may be applying over here. So this is what is a C clamp. Okay, this is how it looks like. It can hold two pieces together. Okay, or it can hold your robot to your table or something like that. A vice also is very much similar, it works in a similar way. Okay, so force exerted on the pieces of wood. So I want to know how much is the interaction force between the wood. Couple required to loosen this clamp. This is another question. How much once it is tightened, force is already known. Okay, I want to know this. Moment is applied, so how much is this force? Got it? So everything is in hand. So couple required to loosen this clamp. Loosen this clamp is a different problem. Tightening is a different problem. Okay, so one is pulling it up, another one is bring it down. So both the analysis will be used here. So let us begin. Mean diameter is this, radius is this, pitch is 2. So given things you have to put in place. Couple for tightening is this. So everything is here. Now the analysis. Okay. So if you use mu, immediately you got something like this. Is it clear? So that is what it is, almost 16.7 that is written here. Okay. Alpha is 7.3 degree. How did it came? So L by 2 pi r. Yes, L by 2 pi r. So that gave me alpha is equal to this. So these are few things that you can immediately get. So moment QR is the applied couple. Okay, so that is this Q into R. So how do you get this? You just divided it by radii. So this is the radii, is it not? Q into R is equal to moment. Q into R is equal to moment is equal to P into A we got. So Q into R, if you divide by moment, you get the effective force that is trying to push it this way. So it comes out to be 8 kilonewton. 40 by 5, that was radii, no? Okay? Okay, so now let us move like this. So while tightening, it goes like this. Okay, this was the tightening scenario. When you have to lift this load, you have to lift this load comes from the top. Okay, load comes like this, you have to go, this should push like this. In order to do that, you have to push it this way, so that you go this way and it gets closer, it gets lifted. So it is against the direction of W. Got it? So now doing the analysis, immediately you just put things in place. You create a force triangle. R direction is given, Q direction is given, W is vertically downwards. I created a force triangle and did this. Considering the tightening case, this is the tightening equation, plus sign if you remember. So tan alpha plus psi s from our earlier analysis, this q by w. So w comes out to be this. Okay. So this is what this w is effectively the force, the clamping force. That is the force that comes, that is the interaction force between them. Both the blocks, they apply that particular force among each other. Okay, so this is there. Okay, now couple required to loosen it, you have to use the other one, that this time you have to apply load like this. Okay, force like this, because you want to bring it down, you want to unwind it, you want to bring the blocks apart, right? So you want to come down. So this is the equation that you have to use. You mind it, this is a negative sign over here that we have considered. This was there from our earlier analysis. You substitute them things in place, draw the vector triangle, draw the figures carefully. So this was there alpha, this is psi s. This time r will be from this direction because friction is in this direction. Okay, r will be like this. Don't try to go back every time you ride on. So effectively this will be your r. Okay, and that is lower than angle of repose. Okay, it is not automatically coming down because you see psi s is greater than alpha. Okay, so that is the reason this equation holds true, and I have just substituted it. I got q is equal to this. So couple will be q into r. So this is the couple. Okay, so external earlier, how much couple did we apply? You question, it was given. It was more than this. So that is the reason why it could bring them together further and create a force. So this is the minimum force which is required to separate them. Okay, so these are the two analyses that I have done. Okay, so using this, there can be multiple numericals that may be given to you. Hope you can do it well. That's all. Yes, you have